All right, so we ended last time, right, with the proof of p-series, and we saw that, right, any p-series where the p-value is greater than 1, it's going to converge. If the p-value is greater than 0 up to equaling 1, it will converge. So now I want to look at some examples of how to apply this. All right, so if you recognize a p-series, you're allowed to just cite it. You don't have to use the integral test to prove it converges, but like I said on the exam, if I do ask you to prove to me a p-series converges or diverges, you don't have to do that formal proof, but you will have to prove it. You just do the integral test on it, and you'll see the result then. All right, so if we have 1 over n squared, this is clearly a p-series, so we would say it converges because it's a p-series where p equals 2. So that's like the minimum of what I need to see. You need to tell me if you recognize a series, what kind of series it is, and what in the series is letting you know that it's convergent. So it's because the p-value is greater than 1. Right? This is also the form of a p-series, right? We know it diverges because it's a p-series where p equals 1, but if you also recognize, right, that that's called the harmonic series, and you just tell me it diverges because it's the harmonic series, that's fine too, because that's a really famous, recognizable series. Just like with geometric series, sometimes we need to rewrite our series so it looks like the form of a p-series. So I would want to see you take this one step further and rewrite it as 1 over n cubed. And now we can see that this is a p-series that converges, right, because p equals 3. So let's look at another example where it's not a p-series. So we have 1 over n times the natural log of n. This does have an n in the denominator, and that n is sort of like the harmonic series, right, because it's only of power 1. So I'm suspicious whenever I see a 1 over n in a series, right? I'm thinking this is probably going to diverge, but you can't just say it diverges because it's a p-series 1, because it's not. That natural log makes it not in the form of a p-series. So for this one, you would have to apply the integral test. So we would need to set up the integral, right? And remember, the bounds on the integral have to match the bounds on the series. So we would have to integrate from 2 to infinity, and we would integrate the function 1 over x ln of x. So a lot of series that have natural log in them, usually the integral test is what you have to do to evaluate them. So as we start getting toward the end of this, right, we said there's going to be certain tells that are going to guide you towards certain tests. Other series, there are multiple tests you could apply. You can just pick whichever one you know, as long as you apply it appropriately. So here, whenever you have natural log of x, you definitely can't integrate that directly, but we can differentiate it. So we're going to let u be the natural log of x. That means I need a 1 over x dx in the integral in order to do a u substitution, and I have one. That extra x in the denominator is going to do that for me. So we said when we're doing an improper integral, right, when we go to evaluate it, we change it to an indefinite integral, which means lose the bounds. And this just becomes the integral of 1 over u du. The antiderivative of this, right, is natural log of u. And when we put back in what u stood for, this is what we're going to evaluate from 2 to b, right? Because you can't actually plug infinity into an equation. So we have to rename infinity some value b. So then the fundamental theorem of calculus says, right, we plug in the top number, then we subtract from the bottom number. So you're going to get the natural log of b minus the natural log of 2. That guy on the right is not the natural log squared of 2. It is the natural log of the natural log. That doesn't multiply, okay? So then this is what we need to figure out, well, what's going on in infinity, right? Since b represented positive infinity, we take the limit of this expression as b goes to infinity. So the natural log of 2 is just a constant. So that's just limit's going to be itself. But for the first guy, what you want to do is you want to look inside the parentheses first. And we say, well, what happens to natural log as b goes to infinity? Well, we talked about last week, well, that goes off to infinity. So now what you've got when you look at the outside function is you're like, all right, well, now I have the natural log essentially of infinity. So it still goes to infinity. So this guy equals positive infinity. And that means it diverges, right? And so if the integral diverges, what the integral test says is the integral in the series will behave the same way. So if the integral diverges, then the series diverges. All right, so this is the end of the section. We'll take the quiz on it on Wednesday, right? And we're going to go ahead and start the next section and talk about comparison tests.